Okay, Joe, let's continue our discussion on equivalence relations. We've been
Okay.
talking about symmetric, reflexive, and transitive relations. Okay, let's
Oh,
start by doing a problem. I'll share my board.
okay.
Okay, can you see the board?
Yes.
Okay, I'll give you an example. You should check whether it is reflexive, symmetric, or transitive.
Okay.
Okay. Okay. Question. Let R be the relation R equals 1, 1, 2, 2, 3, 3, then 2, 1, and 3, 2. Defined on
Mm.
the set. Defined on the set A equals 1, 2, and 3. Okay.
One
So
second.
first, let's tell me whether it is reflexive.
One second. Let me just 3, 3, 2, 1, 3, 2. Okay. A is from A to A.
From A to A, yes. Defined on A.
Okay. Okay. So let's talk about reflexivity. So reflexivity means if a 1 to 1, 2 to 2, 3 to 3. Yeah,
Yes,
reflexive. Yes,
you're
it's
correct. Yes,
reflexive.
you're correct. It's reflexive because the diagonal elements of
Well, it's
transitive
after.
of Cartesian products are all present. 1, 1,
Yeah.
2, 2, and 3, 3 are present.
Yes.
Reflexivity, yes. Then we shall check symmetry.
I don't
Okay.
think it's symmetric.
No, correct. It's not symmetric because here 2, 1 is present,
But
but
1 2 is not present.
it's diagonally opposite elements are not
Are
present.
not present. 3 2 is present. 2 3 is not present.
But no 1, 2 and 3, 2, 3, 2, but no 2, 3. Then finally we shall check transitivity.
One second.
Transitivity can be checked through possible transitive products. We know that. Okay. If all the possible transitive products are present, then the relation is transitive.
Transit. Okay, let me just check 1 1 1 2. I don't think so.
Why?
1. I don't think there are every transitive product is present. XY. Okay, 1. Okay, 2 1 2 3
We
2
can.
2
Okay.
1 1 1. There is no. I can. No transitive products are. Okay, there is no transitive products defined, I think.
If there is no transitive products are not possible,
No.
then it should be transitive.
Okay.
But here 3, 2 and 2, 1 can be multiplied
Yeah, 3 2 and 2 1 can be multiplied, but that should
to
give
obtain
3 1.
3, 1. But 3, 1
But
is
it's
not present.
not present.
Okay. This transitive product is possible. And the product is possible, but it is not present. Therefore, no transitivity.
Yes.
Okay. Therefore, okay, let's check, do another example, an important example. It is also simple example like this. 1, 1. Okay. 1, 2. 2, 1. 2, 2. Then 3, 4. 4, 3. Then 3, 3. And 4, 4. Defined on A equals 1, 2, 3, 4. First, let's check reflexivity.
It's reflexive.
Yes, it is reflexive. Why?
1 second. 1 1 2 2 2 1. Okay. 1 1 1 2. 1 second. All diagonal elements are present.
Exactly.
1 2.
Yes. Here the power is gone and I'm running on UPS. I don't know whether the power will come back. Okay, let's continue. Reflexive. Then let's check symmetry. Okay.
Okay. Yeah. 1 2 1 is present. 3 4 4 3 is present.
We should check the off diagonal elements and whether its diagonally opposite pair is also present.
Yeah, and just reflexive. 1 1 1 2. There is no 1 3.
1 2.
1 3 is not present. So
1 3 should be present if 3 1 is present.
is present. Yeah. 1 3 1 4. 1 second. 1 4. Let me do 1 2 2 2 3 2 4. So 1 for 1 2 we have 2 1.
Yes, for 1 2 we have 2 1. 1 2 and 2 1 is present.
3 4 we have 4 3.
Yes.
Then so there is
So
nothing
yes,
else.
yes, so it's symmetric. Okay, let's finally check transitivity.
Transitive. Let's check 1 second. Yeah, I think it's transitive.
Yes, yes. Okay. This relation is symmetric. First of all, reflexive, symmetric, and transitive. Such a relation is called an equivalence relation. Okay.
Okay.
Such
Symmetric.
a relation is called an equivalence relation. Okay. Symmetric, reflexive, and transitive. SRT. Okay.
Okay.
Okay, Joe.
Yes.
Okay, then that's it. You got the idea?
Yes.
Okay. Well, in fact, equivalence relation is a general notion of equality, if you think about it. Because in mathematics, some things that are equivalent that are not equal in one context may be equal in another context. Okay, equivalence
Could you give me an
relations.
example?
For instance, okay, let's look at another example here. Before giving an example, I'll give you an example. But first of all, let's look more deeply into equalities. Okay.
Okay.
In particular, we have to view equality as an equivalence relation. Okay, if you think about it, we can see that equalities are also equivalence relations. Because what are the three criterions for our relation to be an equivalence relation? Yeah.
Symmetric, reflexive, and transitive.
Yes, reflexivity. So let's look at equality. Okay. We have, we can say that everything is equal to itself. Okay.
Yes.
Okay. So equality is inherently reflexive.
Yes.
Okay, because every object in the universe is actually equal to that object itself. Okay, so equality obeys reflexivity. First, reflexivity.
Okay.
Reflexive. Then let's is equality symmetric, Joe?
Yes.
Yes, because we can say that if A equals B, then we can also write
Then
B
we
equals
also
A.
say we could say
Okay, so equality is reflexive, symmetric, and
and
then
trans.
fine. Yes,
If
yes,
A is equal to
equality.
B and B is equal to C, then A equal to C, right?
Yes, equality is transitive because if A equals B and B equals C, then we can say that A equals C. Similarly, for reflexivity, we can say that A equals A, and for transitivity symmetry, we can say that A equals B, then B equals A. This means that equality is an equivalence relation. Equality is an equivalence relation. Equivalence relation. Okay.
Okay.
Okay. Now let's look at another equivalence relation. I'm going to give you an example. Okay.
Okay.
As a second example, let's consider similarity. Okay. First we considered equality. Now let's consider similarity between triangles. Okay. Similarity. Similarity between triangles. Okay. Similarity
Okay.
meaning all the angles are the same. Okay. Similarity is obviously reflexive because every angle of a triangle, angles of a triangle are equal to itself. Okay.
Yes.
Reflexive because every triangle is similar to itself. Every triangle A is similar to itself. Secondly, let's look at symmetry. 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 If A is similar to B, and then B is
B is
similar.
similar.
B should be similar to A. For
Yes.
instance, let's look at two triangles like this, and both have let's say both have the same angles. Okay, A.
Okay.
This is similar to triangle B. These angles are the same. Then we can
Okay.
say that B is similar to A. Okay, so there is symmetry, symmetry between those triangles. And finally, let's look at transitivity. Transitivity. Okay, transitivity. If A is similar to B and B is similar to C, then we can write. Joe.
A is similar to B. A is
A is
similar
similar to
to C.
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 Meaning, say, let's say we have another triangle here with the same angles, with the different dimensions, but let's say they have same angles. Say C.
Okay.
B is similar to C. A is similar to B, then when B is similar to C, then we can write A is similar to C. Okay.
Okay.
Okay. Now let's look at this idea. Both of these ideas: equality between two objects and similarity between triangles. Okay.
Okay.
Equality is actually a strong relation because equality says that two objects are the same.
Yes.
Okay. Similarity actually is a weak notion of equality.
But yeah.
Okay, because similarity just means that angles are the same. The dimensions need not be same.
Yeah.
Okay, but if we take similarity as some form of equality, in
Okay.
some context we are saying that similarity is equality because we are only concerned with the similarity. We are actually abandoning the distance between vertices or the length of the sides. We are
Sides.
abandoning length of the sides. We are only considering equality between angles
Okay.
or similarity. Okay.
Okay.
Then we can say that in that context, similarity is sort of like an equality. If you only consider that,
Okay.
you get the point. It's actually a tricky thing to understand. Okay, let me like okay, we are actually, I don't know how to put it. Actually, we are actually considering both equality and similarity within a broader context of equivalence relation.
Okay.
Okay, for instance, if this is a broader context, this is some broader set of equivalence relations. Okay, equivalence relations. Relations. Okay, one of the equivalence relation is, we know that equality, which we are all familiar with. Okay,
Yes.
another equivalence relation is similarity. Okay, similarity is not equality, we know that. But
Yes.
if we as a broad, if we generalize the idea of equality,
Yeah, we can say that.
for considering some weaker notions of equality like similarity. Okay,
Okay.
because
Then it's an
similar,
equivalence.
then it's like a tricky thing. It's like a broader viewpoint of idea of equality.
Okay.
Similarity is an equality, but only if we consider equality between angles.
Okay.
Okay. For instance, are you familiar with modular arithmetic, congruency between numbers? Moduli operator. I heard you talk about moduli operators in C programming or something.
Absolute.
No. Moduli. When you were talking about the algorithm for credit card numbers or something like, you talked about
Yeah.
moduli operators. Do you remember?
Modular. Yeah, modular
Reminder
operator.
operators.
Yeah. Yeah. Yes.
Okay, that is
Yeah. That.
actually a no, that is an actually equivalence relation.
Okay.
Okay,
Yeah.
if for instance, that is actually detour from our discussion, but we can say that let's take a number 4. Okay. Okay, let's divide all the integers with 4 and take the remainders. Okay, when we divide 0 by 4, the remainder is 0. For 0, r equals 0. Okay. For 4, also the remainder is 0.
Remainder is 0.
For
For
5, the remainder is
the
1.
remainder is 1.
For 6, the why is the remainder 1? Because 5 can be written as 4 times 1 plus 1.
Plus 1.
Similarly, 0 can be written as 4 times 0 plus 0.
Plus 1.
Similarly, 1 can be written as 4 times 0 plus 1.
Yes.
So in terms of division, when we divide 1 by 4, the remainder is 1 in that context. Okay.
Yes.
Similarly, 2 remainder is 2, 3
It's 2.
remainder is
Remainder is 3.
3 remainder is 3, 4 remainder is 0, 5 remainder is 1, 6 remainder is 2. Okay. Okay, Joe.
Okay.
Okay. So in this context, if we look at only reminders, okay, for instance, for what is the remainder of remainder when we divide 9 by 4?
1.
Okay. Here 5 has the same remainder, 9 has the same remainder. So in this context, we say that both of these are equal. In this context.
Oh, okay.
Okay, if you consider only reminders. That kind of arithmetic is also known as modular arithmetic. It's very, very important computer science. Computer science, which is at the core of computer algorithms and programming, modular arithmetic. I heard you talk about this when you considered coding, like coding about credit card numbers. I'm not familiar with the algorithm, but I heard you talk about this thing. Okay, modular arithmetic. At the core of modular arithmetic is the idea of equivalence relations. We are equating two things only based on equality of remainders.
Okay.
But if we strictly consider equality, the 5 is not equal to 9. We know that. But
Okay.
if we consider remainder, when considering 4, remainder with the 4, we can say
Okay.
that both of that is actually written as 5 congruent to 9 mod 4. If you, I don't know if you heard about this notation. This says that when we divide of both 5 and 9 with 4, the remainder is same.
Okay.
That is a
So
notation.
it's like different kind of algebra.
Yes, it is actually very important algebra. This is actually a group.
Okay. So
This is
okay.
actually
So
a group.
you asked, yeah.
Okay, this is
It's
actually a finite cyclic group.
different.
Very important group. Okay.
Okay. So what you are saying is that the notion of equivalence will depend upon the algebra we are using.
Algebra or the
The
context we are
Yeah,
in.
yeah. So in different contexts, we are using different algebra. For example, in the modulus, we are using in the context of modulus, we are using a different algebra. And also, we can say in the similarity of triangles, we can say the similar operations, or that in that context, we can say
In
similarity
similarity
as an
of
equal.
in similarity of triangles, there is no algebra. Okay,
Or no, there
equivalence
is no
relation
algebra.
is actually not
Okay,
just
in that, it's in okay. That's what you mean by context. Okay,
okay,
I
okay.
understood.
In equivalence relations are beyond algebra. It is not only constrained with the algebraic
The
things,
way it's also concerned with geometry of the.
geometry also, but in
Mm.
general, we can I call equivalence relations as context dependent equalities.
Yeah, we can say.
Okay, equality that depends on context. In this context, we can say that they are equal.
Okay.
Okay, in that context, that's very important idea in mathematics, because things that are different in one context may be equal in another context.
In another context,
That
yeah.
notion is made concrete by the idea of equivalence relations. Equivalence relations makes that concept more mathematical.
Okay.
Okay, it is actually a tricky thing to understand. You have to think through it very carefully. Okay, equivalence relations are generalized notions of equalities. Equivalence relations are
Generalized.
generalized notions of equality. Generalized notions equality. Very important idea. If two things are equivalent, it is equal in some context.
Some context.
Okay, we can consider them equal in that context only. It's a very important
That's
idea.
a no. That's a
Okay, Jeff.
novel idea.
That's not a novel idea. It's
I know
well
for
known
me.
from some people may never understand this idea when hearing for the first time. Okay, you have to
Yeah.
think through this idea. Okay, it generalizes notion of the equality. What do you mean when we say that two things are equal? It depends on what context we are talking about that equality. So okay, in that way, equivalence relations are general. It generalizes the idea of it. You have to think
Equality.
it through. Okay, very important idea in
Yeah.
mathematics. Okay, so let's the next idea here is the idea of equivalence class. Equivalence class.
Okay.
E-
Equivalence
e-
class.
Equivalence classes. Equivalence classes are equivalence classes. Equivalence classes are set of objects that are equal under this equivalence relation. This generalized notion of equality. Okay, that becomes clear when we look at when we do this example. Consider an equivalence relation R equals 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, 3, 2, 4, 3, 1, 1, 3, 2, 4, 3, 1, and 4, 2. 4, 2. Defined on the set A equals 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. First, let's check whether it is an equivalence relation. Joe, is this an equivalence relation?
Let me just look at it. Reflexive.
Yes, it's reflexive.
For sure. Okay, then yeah, symmetric 1, 3, 3, 1, symmetric 2, 4, 4, 2. Yes, okay. 1, then 1, 3, 3, 1, 1, 1 is there. 2, 4, 4, 2, 2, 4, 2, 2, 4. Yeah, it's equivalence.
Equivalence relation. Okay, let's take an element of this set A. This set is important. Okay, let's take an element. Let's take an element of A. Okay, say 1. Let's take the first element. Okay, and let's consider the elements of A that are related to 1 under this equivalence relation.
Okay. So
let me denote that by putting 1 inside a box. This means that set of elements of
related to 1.
Element of all, meaning set of objects that are equal to 1 in this context. That's the idea.
Okay.
Set of elements of A that are related to 1. For that, let's look at the ordered pairs containing 1 and what all other elements are present in those ordered pairs. What are the ordered pairs that contains 1? Ordered
1, 1, 1, 3, 3, 3, 1.
Okay. Ordered pairs that containing 1 are 1, 1, 1, 3, 1, 3, then 3, 1. So what elements are related to 1?
1 and 3.
Exactly. Set 1 and 3. This is known as equivalence class of 1. Okay, equivalence, EQUIVA, equivalence class of 1. They are set of elements that are equal to 1 in this context.
Okay.
Meaning in this context 1 and 3 are same.
Okay.
In what context? In the context of this equivalence relation.
Of this relation.
That is a very, very important idea. Very, very important idea. meaning here that term is important because only here 1 and 3 are the same, are equal, because 1 is equal because due to this thing, equality means equality obeys all of these three things, correct?
Yes.
And those three things are also obeyed by this relation also.
Yeah, it's like
okay.
So
this is also an equality. but in some weird context, some weird type of some other kind of sense, this is also equality.
Yeah.
It's very interesting, isn't it, Joe?
Yes, it's very interesting.
Okay, so equals the class of 1 and 3 is the set 1 comma 3. Okay, so what will be the equivalence class of 3?
3 and
Because
1.
because they are the same, because 1 and 3 are equal.
Yeah.
Okay, okay, then let's look at another element. Let's look at let's find the
2.
equivalence class of 2. Okay,
4 and 2.
okay, 2 and 4, which will also be the equivalence class of
4 and 2.
no,
4.
4. Exactly. Okay, okay, 1, 2, 3, 4. Then what is the equivalence class of 5?
5 itself.
5, exactly. Okay, so we can write. Okay, so we have got all the equivalence classes. We have got equivalence class of 1 equals 1 comma 3. Equals class of 1 is also the equivalence class of 3 equals 1 comma 3. Equivalence class of 2 is also the equivalence class of 4 is 2 comma 4. Then we have equivalence class of 5, which is the number 5 only. Okay, okay, now let's take the union of these two equals, these three equivalence class.
It will give the set.
Exactly, take the union. 1 union 2 is okay, 2 union 5. Okay, that's it. 3 is also 1.
Yes.
Okay, Joe, are you following me?
Yeah. Oh, yes.
Okay, Joe, write it. I'll continue after you.
Oh, I am writing. 1. It will be equal to A.
It will be equal to A. Also, if we write A as the set 1 comma the set 2 comma the set 5, we get a partition of A, isn't it? Because we get 1 comma 3 comma 2 comma 4 comma 5. This is actually partition of A.
Partition meaning?
Partition means dividing into subsets, but when we take those subsets should be no element should be common to both two of those subsets. Okay, intersections should be null set. For instance, if we take partition means, for instance, 1 union 2 union 5 should give A, and 1 intersection 2 should be null set.
Okay.
Okay, similarly 2 union 5 should also be null set. Similarly 1 intersection 5 should also be null set. Okay.
Okay, 1 second.
Okay, meaning the subsets are disjoint. Partition is splitting the set into disjoint subsets.
Okay.
This is a partition. Partition meaning splitting the set
A into disjoint subset.
disjoint subsets whose union should be the set itself. Subset whose union is the set. Okay. So we can write A as set 1 comma 2 comma not A. This is not A, this is a partition. And this is the partition of A. This is the partition of A. Partition of A. 1, 3. And that partition is called quotient. Okay. That partition is called quotient. Okay.
So, okay.
Also written as A A mod R, meaning we are dividing that set into equivalence classes of R.
Okay.
Yeah. A mod R,
Okay.
quotient, also known as quotient set of A modulo R. Quotient set of A modulo R, also written as A mod R. Okay, it will be clear when we do another example. Or should I talk about it one more time, Joe?
No, I got it.
Okay, the idea is simple. We took an equivalence relation. Then we found out the equivalence class of all of those elements. Okay, and we so found that equivalence classes actually form a partition of that set. Okay, that partition is the set of equivalence classes, isn't it?
Yes.
That set of equivalence classes is also known as quotient. Quotient set of A modulo R, also written as A mod R. Okay, let's do another equivalence relation. Another equivalence relation. Set 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, then 1, 2, 2, 1, then 1, 3, 3, 1, then 2, 3, 3, 2, then 4, 5, 5, 4. This is an equivalence relation. Okay, the question is find the equivalence classes. This is defined on A. This is defined on A equals 1, 2, 3, 4, 5. 3, 4, 5. Question is find the equivalence classes. Find the equivalence classes and write A mod R. Write the quotient set of A modulo R. The quotient set. The quotient set of A modulo R, also written as A mod R. Okay, Joe, find the equivalence classes.
For 1 it is 1, 2, 3.
Yes, exactly. So 1 it is 1, 2, 3. So that will also be the equivalence class of what?
2.
2 and
3.
exactly. Okay, secondly 2, 3, we got the answer. Then
4 it is 4 and 5.
Exactly, for 4 we have the set 4, 5, which is also the equivalence class of
5.
5, exactly. So we can see that if we take the union of this thing, for instance, 1 union 4, what is the set resulting in that union?
1, 2, 3, 4.
1, 2, 3, 4, 5. Yeah, yes, the set
5.
A itself. Okay. And we can also see that 1 intersection 4 is
0.
a null set. So this is a partition.
Yes.
Okay. That actually is a test for whether it is an equivalence relation.
Okay.
Okay, to check whether a relation is equivalence relation, we have to find the equivalence classes and show that that forms a partition.
Okay.
Okay, that's also a way for showing whether a relation is an equivalence relation or not. Okay, then what is the quotient set? What is A mod R?
A model is a modulo. Sorry. One. Set 1, 2, 3.
Set 1, 2, 3.
And 4, 5. Set 4, 5.
Set 4, 5. Meaning the set of equivalence classes. That's it.
Yes.
Set 1, 4. That's it. Okay. You got the idea?
Yes.
Now look at this, Joe. This set 1, 2, 3 are represented by 1. It's only 1. We can
Okay.
also write this as 2 like 2, 4 also.
2, 4.
Okay,
Oh, yeah,
because
2, 4 to 3, 4 or 3, 5 or
5,
anything like
yeah,
that.
exactly. Because in this context, 1 and 2 and 3 are equal.
That's equal.
Do you get the idea
Oh,
here?
yeah, yeah.
That is what I meant by saying that equivalence relations are generalized notions of equality, context dependent equalities.
Yes.
In this context, 1 and 2 and 3 are the same.
Yeah, it's like if you want to give a physical representation, we can say elements, or if I have a piece of 1 kilogram piece, 1 kilogram piece of iron in India and a 1 kilogram piece of iron in Germany, they are the same in the context that they are iron. If that 1 kilogram is a knife in my hand and other thing is it's a block of 1 kilogram, then it is
Whatever the context can be any, it can be any context.
any kind.
Okay, but
Yeah,
if it's defined properly, and we can
can.
and if you are able to show reflexivity, symmetry, and transitivity, then in that context, it is an equality.
Yeah.
But you should be able to show that it should be reflexive, it should be symmetric, and it should be transitive. Okay, this is called quotient.
Yes.
Quotient. Very, very important idea. Probably one of the most important idea in mathematics. Okay. And let's conclude by discussing one more thing, which is it's basic idea, but let's look at that idea also, and let's conclude our class today. Okay, Joe?
Okay.
Okay, so let's the idea is a quotient called quotient theorem. Quotient theorem. Okay, I could have just stopped here, but this is a very interesting and very, very fundamental idea. Quotient theorem. For that, let's look at a function. Okay, let's look at a function. Let's look at a function. Function f from a to b. Okay.
Okay.
Let's draw that function. 1, 2, 3, 4, 5, 6. Okay, Joe.
Okay.
Okay. Here, let's consider another set B, A, B, C. That's okay. A, B, C.
Okay.
A, B, and C. Okay. Let's map 1, 2, and 3 to A. 4 and 5 to B. You can take any function, it doesn't matter. I just took an arbitrary map.
Okay.
Okay. This is A and this is B, and this function is F.
So you are mapping 1 and 2 to B.
1, 2, and 3 to A.
Okay. Then 4 and 5 to B. And 6 to C. Okay.
Okay. Now I'm defining a relation. You should tell me whether it is an equivalence relation or not. Okay. I'm defining a relation on A.
Okay.
Relation let's look use the symbol tilde. Okay, we can also use R because I have used R for all these relations. For a change, I'm using the symbol tilde, which is defined on A. Okay,
Okay.
set of ordered pairs x comma y, where f of x equals f of y, meaning both x and y have the same image in B,
Okay.
where x comma y are elements in A. This is the relation. You have to check whether this is an equivalence relation. I'll add a page below, down below. Okay.
3, 3, 4, 4, 5, 5, and 6, 6. Then you will have 1, 2, and 2, 1. Then 1, 3, and 3, 1. Yes. Then 4, 5, and 5, 4. Then that's it. Yeah, it's an equivalence relation.
Yes, because what is what is the relation here? The relation says that two objects are related if and only if both of them
X.
have the same image. Okay.
Yes.
We can easily verify the reflexivity, right?
Yes. Yeah.
Because reflexivity, because okay,
One come.
because f of x is always f of x.
Mm.
Okay, and then symmetry, because if f of x equal to f of y, then f of y is also equal to f of x. Okay, symmetry. If f of x equals f of y, then we can say that f of y equals also f of x. Okay.
Yes.
Then finally we can say that transitivity. F of x equal to f of y and f of y equals f of z, and we can say that f of x equals f of z.
Yes.
For instance, 1 and 2 have the same image, 2 and 3 have the same image, therefore 1 and 3 have the same image. That is transitivity.
Yes.
Okay. So this relation, meaning relation defined as two objects should have the same image. That relation is an equivalence relation.
Equivalence relation.
Okay. So find the equivalence classes of that equivalence relation.
Equivalence class.
This is an equivalence relation. This is tilde is an equal. Tilde is okay. Now find the equivalence classes. Okay, let's pick an element. Okay, Joe.
Yes.
First, let's pick. What should we
One.
pick? Okay, let's pick one and find the equivalence class of one. What are the
1, 2,
equivalence?
3.
Exactly 1, 2, 3. Therefore, this is also the equivalence class of
2 and 3.
okay 2 and 3. Exactly, because both 1 and 2 and 3 have the same element.
Same.
Okay, so in that context, meaning in what context? Being same image in the that is the context here. In that context, these are the same because these. Do you understand that idea? Generalized
Yes.
notion of equality.
Yes. It's like an. It's like.
It is actually hard to describe in words, but okay.
Yeah.
Do you understand that it's actually
It's
more
like
like
a
it's
person
intuitive
being
notion.
color. It's like a person being colorblind. No,
Oh,
some people can cannot distinguish certain colors. So
that is a wildly stretched and exaggerated idea.
I know it's
Okay,
like it's very similar because if I show him a red apple and suppose he cannot distinguish between red and yellow. Okay, so if I give him a red rose or a yellow rose, it is same to
okay.
him.
To him, both those
In
roses
that
are same.
context, yeah, in that context,
Okay, let's hope no color-minded person is watching this video. Okay. Okay, and what are the equivalence classes of, what are the other equivalence classes, Joe?
other equivalent classes four and
Okay,
five are equivalent
okay.
classes.
Equivalence class of 4 is 4 comma 5, isn't it? Because
Yes,
both 4 and 5 have the same image here.
image here.
Then equivalence class of
6.
6. Okay, is just 6. Okay, so then what is the quotient of this equivalence relation? Meaning, what is A mod tilde? What is it? We can
It
write it
is
as
1, 4,
uh,
6.
1 comma equivalence class of 4 comma equivalence class of 6. Okay, now
Yes.
let's really look at, you should really look into it very carefully. Okay,
Okay.
I am actually going to make going to make this map, going to decompose this map. Okay,
Decompose mean?
meaning, let's first look at the set A here. Okay,
Okay.
we have 1, 2, 3, 4, 5, and 6. And
Okay.
we know that both 1, 2, 3 are all mapped into A.
Yes.
Okay, so before making this map from A to B, I'm first making a map from A to A mod this equivalence relation, this quotient. This
Okay.
map is called quotient map.
Okay.
Okay, what is the quotient set? Quotient set is 1, then
1, 2, 4,
4. Okay, we have 1 here, we have 4 here, we have
6.
6 here. This is the quotient set. This is our original
Mm.
set A. From our original set A, we are first making a quotient map, meaning mapping to quotient. That's called quotient map. Okay, so
Okay.
these 3 will get to this 4, 6 to here, and then I am going to plot it into to the image of that function.
Okay.
For instance, what if there was an element D here? Let's
Okay.
assume there is an element D here, but nothing is mapped to D.
Okay.
Okay, so first then what will be the image set of F? Image set of F. Image of F.
Image of F will be the same.
Set
A, B, A, B,
A, B, and image
C.
set of images.
A, B, and C.
Yes, exactly. Let's consider here image set. Image set is the set of images of F. Okay, that image
Okay.
set will be A comma B comma C. This is set. Okay, so we have
Okay.
A here, B here, and C here. So we know that all 1 comma 1, 2, and 3 maps to A.
Yes.
Okay, so before that map, we have mapped those 3 elements to the equivalence class. Then we are mapping that quotient set to image set.
Image. Okay.
So it should be a bijective map,
Okay.
isn't it?
Yes.
Then finally, I am mapping this image set to your initial set, to our final set B. That map is just a inclusive relation, subset relation. Because
Okay.
what is the set B here? Set B is
A, B, C, D.
yes, A, B, C, and D. This is just a subset relation, because this set is actually a subset of this thing. Because image set sheet is always a subset of the codomain, isn't it?
Yes.
So that is a natural. That's also not. That's why it's also known as natural inclusion. It's naturally included in B. This is an inclusion. Inclusion meaning subset. Included. Inclusion. This is a quotient map. Okay. Joe, write this. Let me make it this diagram to the center. Okay, this is very. Oh, gee. Okay, Joe.
Okay.
First, we made a quotient map to A mod that equivalence relation to the quotient set. Then we made that. Okay, let's look at that map first. This is always a surjective map, meaning many to one map.
Yes.
Okay, this is always a surjective map. Also, surjective maps are also known as epimorphisms. Surjective or epimorphism. Surjective or many one or surjective, right? Many to one, many one, many one, or surjective or epimorphisms. Okay.
This one, quotient maps. You're talking about quotient maps,
Quotient
isn't
maps.
it?
Yes, quotient. Surjective, also known as epimorphism. That's also another name for not another name, but it's general notion of surjective map. These are also generalized notions. Epimorphism. Epimorphism. Surjective map is a kind of epimorphism. Okay. Now, what is this map, Joe? This is always a one-to-one map, because this is just a subset inclusion. Okay, this is always a one-to-one map. One-to-one.
From
image to image to
quotient to
the image to codomain. This map, final map. I'll talk about the center map, the map that is in the middle, that I will talk about last.
One-to-one is a bijective, isn't it?
Yes, bijective. No, injective.
Injective. Yeah.
Injective map. Okay, this is also known as monomorphism. Monomorphism.
Okay.
Okay. Now this is both one and onto.
Yeah.
Okay.
Okay.
Okay. No, not many one, Joe. I made a mistake. This is onto map. Onto map. Onto. This is onto. It's a many one, but it's always an onto. It can be one-to-one map also. That was a mistake I made. This is an onto map. Okay. It can also be a one-to-one map. It is one-to-one or many-to-one. It doesn't matter, but it's always an onto map.
Okay.
Finally, this map will always be an bijective map. Bijective map, meaning one to one and on to. Okay.
Okay.
Bijective map, also known as isomorphism.
One to one and on to.
On to. One and on to map. That's called a bijective map.
Okay.
One. This is on to. One and on to is bijective. I usually don't use this one on to. I usually only talk like injective or surjective. Okay.
Okay.
We should always. It's confusing. Like, okay, this is surjective. This is injective, and the center map is bijective.
Okay.
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 Okay. Bijective map is also known as isomorphism. Okay. So what we have done here is that we had a function a to b, and f. Okay. And we have decomposed that function. As first we made a map from A to the quotient map. What quotient is this? This is a quotient of equivalence relation defined as equality in terms of same image.
Same image. Okay.
Okay, that is, so we the quotient should contain the equivalence classes of that equivalence relation, and we just map that set on into the that equivalence relation. Okay.
Okay.
Then we map that equivalence classes to the images. Then we map that image set into our codomain.
Yes.
That is, we can write A to B, this F, as first we map A to A mod, that equivalence relation. Okay.
Okay.
Let's name this map as G. Then we map that quotient to the image of that function, imager. I'll write this as an I. Then we map this to the image to the codomain. This is just H. Or we can write F as H of I of G. H after I after G.
Okay.
We can compose this.
Okay.
This way of decomposition is true for any function. This is also known as universality. This is a universal property. Universal property. Also known as quotient theorem or first isomorphism theorem. This diagram, this commutative diagram is known as first isomorphism theorem. This is a universal property, meaning true for any map. True for any function. Any function can be decomposed as this. Any function.
Okay.
Also known as first isomorphism theorem.
Or quotient theorem.
Or quotient theorem. Decomposed as a surjective, injective, and bijective. Okay, surjective means on to, injective means one, and bijective means one and on to. Okay.
Okay.
This was actually discovered by Emmy Noether.
Noether's theorem.
This is actually also known as Noether's theorem. Emmy Noether first discovered in the context of group theory. Actually, discovered in the context of group theory. Discovered in group theory. Okay. which is why this is actually widely considered as most important theorem in algebra. Most important theorem in algebra. Most important theorem in algebra. But we are discussing just in terms of sets and maps. We have not discussed group theory or any algebraic objects. Okay, this actually was discovered in group algebra, but then it grew out of algebra into a wider and general context. Now it is actually viewed in terms of universal algebra or category theory, or kind of these abstract general theories. This has become a general. This is true for any map. That map can be an algebraic homomorphism or topological homeomorphism, any map, or just a mere map between two sets.
Okay.
This is true for any map. Any map can be decomposed as a quotient map followed by an isomorphism. This is an isomorphism. This is an isomorphism. Isomorphism. Followed by an isomorphism followed by a natural inclusion. This is a just injective surjective. I think surjective maps are also drawn like this. I actually don't remember. Okay, also known as canonical decomposition, also known as first isomorphism, also known as canonical decomposition.
Okay.
Canonical decomposition. Okay.
Okay.
This is true for you just take any function. Any function can be decomposed as this. First define an equivalence relation by defining two sets equal when they have the same image. Okay. Then find the equivalence class of that equivalence relation. Then map the set to that equivalence class. Then from that equivalence class to the image set, then that image set to the codomain. You get the same map. Okay. This was a brilliant breakthrough in algebra. I think in 1927, something like that. I don't remember the exact year when she found this. Okay.
Okay.
This isomorphism, we can actually summarize this entire thing as just this isomorphism. Domain mode, this equivalence relation is isomorphic to image. That's it. This is the idea. This is the first isomorphism there. This isomorphism. Okay. Do you have any doubt here, Joe?
No.
Okay. This class. Actually, we have looked into very deep kind of ideas here. Okay. Okay. Do you need a minute to recollect?
I don't think so, but I think I got it.
Okay, Joe.
Okay.
Okay, so we are concluding our discussion with this equivalence solution and equivalence classes because we needed these ideas because when we move on with our discussion on algebraic geometry, the idea of quotients come up very regularly. Okay. And we have to be um, uh, we have to have that idea of generalized equality. We are considering, in the next class we will be studying about affine transformations, and we can find that we can prove that affine transformations are equivalence relations. Okay. And the equivalence classes of that affine transformations are the conic sections.
Okay.
Very important idea. And we can see that circle and ellipse are belongs to same equivalence classes, meaning under affine transformation both of them are same. That is why we always say that circle is an ellipse.
Okay.
That is in this context. This is very important ideas coming up. That's why I discussed these ideas here. Okay. So let's conclude our discussion. The first isomorphism theorem is actually not needed for our upcoming discussion. But anyway, I discussed it because it's very foundational idea in mathematics. Not only in algebra, not only in algebraic geometry, it's foundational idea in mathematics, the universal idea in mathematics. Okay. Okay, Joe. I'm stopping my recording.